by Oscar Guajardo from Mathematical Institute. We will talk about the straightening of smooth least groups.
Yes, something of the sort. Thank you very much. And, well, happy birthday, Adolfo. Thank you for having me here on this celebration of your work. Well, he was a jury in my master's thesis, and so this is sort of a continuation of what I started in my master's. And, well, first of all, I have to apologize. Given the time I have and the nature of the problem I'm tackling, I will owe you all the examples. I mean, the examples are just the obvious ones. That's the problem with all the things I'm doing right now. So, okay, the first two parts are more or less a summary of what I did on my master's thesis, and then I'm going to go talking about Lie supergroups, which is what I'm doing in my PhD thesis. And well, I think this slide is it doesn't belong here. You all follow the right faith, but yes, everything is smooth. Everything I will talk about will be finite dimensional and real. Okay, so let's start with supermanifolds. Our definition of a supermanifold differs somewhat of the usual definition in that we don't use sheaves for it. We use an algebra bundle, and well, the definition is the usual thing. M is a usual classical m-dimensional manifold, and Rm is a unital superalgebra bundle over that manifold, meaning that every point is isomorphic to the exterior algebra of a vector space of dimension n. The p there is I slipped. That's a typo. It doesn't depend on the point p. And well, the sections of this bundle we call the smooth superfunctions. Okay, so one of the things is that the bundle Rm is not necessarily an exterior algebra bundle. Okay, that's the first thing. And the second one is we still get a filtering of the algebra at each point, and therefore at the level of sections and at the level of bundles, by considering the nilpotent bundle at each point. Now and then taking the powers. Right? So this is fairly simple, I think. And now I have to tell you what the smooth maps, the smooth supermaps are. And well, the definition is again quite straightforward. First, it consists of two parts. The first one is a usual smooth map between two manifolds, and the other one is it goes the other way around. This is necessary, and it's a unital homomorphism of superalgebras. That means that one goes to one, and this forces the morphism to be even. So now I can tell you something about these things, and we can define these commutator. Okay, all of this makes sense because this is a section of a vector bundle. This is also a section of another vector bundle over another smooth manifold, but this is a function over that manifold, and we can prove that. Well, first of all, that this iterated commutator is independent of the order in which you insert smooth functions, and if you exceed the integer part of q over 2, where q is the odd dimension of the codomain, then you get 0, and that's why we call them. We say that big phi is a differential operator along little phi, meaning that if m equals n and little phi is the identity, we recover a characterization of a linear differential operator. Okay, so that's for morphisms, and well, one of the important theorems that we proved. This part is known as a bachelor's theorem, although we gave another proof of it. What this theorem essentially says is that it doesn't matter as long as we consider smooth real supermanifolds. The usual sheaf theoretic approach and our approach are exactly the same. It's the same theory. So I actually was quite startled by this theorem, but fortunately it is true. And well, this part takes care of the morphisms, and well, this part is bachelor's theorem, which takes care of the objects. So now I can now we can go up to the infinitesimal level. And this part I actually like quite a lot. So if we have a supermanifold, we can define what I call odd directions and codirections, which the name forces itself once one looks at the definition, because on a regular manifold, what we have is the directions are what we call tangent vectors, and the odd tangent vectors would be the ones pointing upwards, right? So those would be the odd coordinates. And well, once we have a supermanifold morphism, we can patch up a vector bundle morphism between these two exterior powers, which are defined essentially the same way with appropriate indices over there. And since every talk has to contain at least one proof, here's a proof. No, this is true because phi preserves the filtration of the algebra. Okay, so it descends to the level of bundles. Right. So this is the important part. As in usual differential topology, we need to define the differential or the tangential maps, and it's actually quite easy with the previous proposition. What we get is the differential, the one that goes in the right direction, is defined by this, and you will notice that we have the usual tangent bundle, that makes sense, and the bundle of odd directions. That should make sense, and it does, because I will tell you a result later that tells you that at least pointwise the bundle of super derivations, which is going to be a bundle, is generated pointwise by these two bundles. Okay, meaning that every super derivation I can completely characterize what happens to these two parts. Okay, so you can consider these to be the even part of the super derivation, and this one the odd part. And well, the codifferential is just the dual. Well, that still makes a lot of sense. And we get a very important map over here, which we call the auxiliary differential. And it's defined by this formula, which makes sense also, pointwise. And well, of course, we are using the fact that we can, around a point, we can write every differential one form as the differential of a function. I'm sorry, and well, this makes sense, and it's going to be quite important when I discuss the multiplication map of a Lie supergroup. Okay, so and well, we also have actually the one that will be useful to me will be the dual of this one. Okay, and we call it the auxiliary because we couldn't think of a better name. But anyway, so and now finally, the promised result about the tangent superbundle. The first thing we have to observe is that at each point, in a regular manifold, in a classical manifold, the fiber of the structure bundle is just a real line, and the derivations of the real numbers are just zero. But in this case, we have non-trivial derivations at each point. These derivations only act on the fiber of each point. So it makes sense to form a bundle out of them, right? So that's what this bundle is, okay? Well, fiber-wise. And the theorem says that we can characterize the super derivations of the superalgebra of superfunctions is the sheaf of sections of a vector bundle over M, no, that is characterized by this exact sequence. Okay, this is just regular inclusion. This is something called a principal symbol of a differential operator. Okay, this is a very nice theorem, I think. And well, all of these will be appearing in Colloquium Mathematicum shortly, I hope. And it's also on the archive. This is the name of the paper. And now we can go to what I came here to tell you. So Lie supergroups. First of all, well, Okay, let me just continue. First, there's a special kind of supermanifolds. We call them split, and we denote them by this because they are completely characterized by either the bundle of codirections or of odd codirections or odd directions. Okay, we don't need anything else to know what happens when treating one of these manifolds. So the name comes from Bachelor's theorem, and it has an algebraic motivation. But what we can prove, and this is quite nice, that a split supermanifold is a Lie supergroup, whatever that means, if and only if the manifold is a regular Lie group, which ought to be, and the bundle is GB homogeneous, meaning that we have this diagram, we have this map, that's why we have this. We have this map we call a B-action, no? which is essentially a pair of actions, one right action, one left action, and they commute, okay? They intertwine well. And of course, G has a natural B-action on itself by right and left multiplication. Those also commute, and the B homogeneity comes from the commutativity of this diagram. Okay, and we can also prove that these objects, GB homogeneous bundles, are in complete correspondence with representations of the group. So we are back onto the realm of representation theory, which is usually quite a good thing, no? And well, the thing is that Lie supergroup in this split category it should be a group on a category, right? It should be something like this, no? It should be an object of the category with three maps, three distinguished maps that satisfy the group axioms, which can be phrased in terms of commutative diagrams. And that's what happens. In the split category, we have no problem. They're in correspondence with B homogeneous bundles. The problem here is that, well, first the consequences, G should be a Lie group, no? The bundle of directions, of odd directions of this supermanifold is also GB homogeneous. That's also easy. The tangent space, or the supertangent space at the identity element is also a Lie superalgebra. That's more or less easy to prove. But the problem is that the bundle RG is not necessarily B homogeneous. There is no natural way, there is no straightforward way of defining a B action, which is kind of regretful because in the split category, we could write down a dictionary between supergroups and representations of the group. And in this case, we can't, well, not naturally at least. But when we have the multiplication map is a smooth supermap with very special properties, but the dual of the auxiliary differential of that thing is a map that goes from this bundle, the second exterior power of SG plus SG, to the tangent bundle of G. Now, and it behaved in the sense that we can recover the Lie algebra structure from that map. And what we do, first, this lemma just tells us what happens at the level of the auxiliary differential when we consider the composition of two maps. And the second one, well, it's a very complicated computation, but what it says is that the auxiliary differential and the B action interrelate in a very nice way. The B action is codified in the differential of the multiplication. I forgot to say that. In the category of split Lie supergroups, one only needs to define the differential of the super multiplication map, and that completely characterizes the whole map. Okay, because it's a bundle map in the end. In this case, it's not necessarily a bundle map, but it still has a proper differential. We can make it act with the auxiliary differential of the multiplication, and we get well, this for this and this for this, no? And owing to some miraculous so, well, first, owing to some miraculous cancellations, what we can do is writing any element as a product of two elements of the group. We can always do that. We can define this map. Beta is the B action, okay? So if you notice, this S and T will be over the fiber of this element, xy. This guy, what beta ESY inverse does is forget that it was ever over y and just put it over x. And this guy, what it does is forces T to forget that it was ever over xy and just put it over y. Okay? We're multiplying by the right and by the left by the appropriate elements. Okay? So this is in the right fiber. And this turns out to be a bilinear map, and we can polarize it, and we get a symmetric and a skew-symmetric maps from this. Okay? But we still need to decompose G as a product of elements. And the thing is that that decomposition turns out to be material at the for the symmetric part, because we know that the auxiliary differential should be a skew-symmetric map. So the symmetric parts just die. Okay, they cancel, and we recover a B equivariant bilinear symmetric map from the fiber of the bundle of odd directions at the identity to the tangent to the Lie algebra. Well, I should have written it that way. So this is good news, because we have a theorem that completely characterizes Lie algebras in terms of three sets of data. Well, first, I'm sorry, Lie superalgebras. What we need to know what happens to what we need to know to construct a Lie superalgebra are three things: a Lie algebra, that makes sense; a representation of the Lie algebra on the odd subspace of the supervector space, and a symmetric bilinear map that satisfies all this. Okay, and this is a way of codifying the graded Jacobi identity. Yes. So if we have this and further for the multiplication map, we already get for free. Well, not for free. We had to do a lot of computations, but we already have one of the maps required by this theorem. Then we get what we need. We get a first. We can define on the split Lie supergroup a new multiplication that is not a bundle map, but nevertheless is well defined. And we get, well, this turned out to be quite difficult to construct, but we get a differential operator from over the identity of the Lie group, no, that intertwines the two multiplications. And that's a very good thing. What this theorem says is that, well, we had a nice category, in which objects were completely codified by representations of a Lie group, no, and we have another category in which we don't know what is happening, but we have a natural way of intertwining the two of them. Okay, and this is natural. This is just God-given. Okay, so that's essentially the main result of my current work. It's joint work with my advisor, Gregor Weingart, which is seated over there. And, well, I think that's all I have to say about it. Thank you very much. Complaints?
Would it be, some of the things that you did for your approach to these groups,
yeah,
can be put in the language of homogeneous vector bundles.
Yes.
Vector bundle over G, an action with a G action.
Yeah.
And do you have something like even?
This is not me, okay? Do you have something like what?
Yeah, I mean, given if you're given a group
Yes. Yeah. So, right. So, like this.
Do you need something else to produce a supergroup, or how many supergroups?
Yeah, that's a very good question. Well, the thing is that from this action, okay. For instance.
I was going to say is that kind of approach, posed that way, I guess it's it has been known for
Yeah, decades. Yeah.
time. So can you give the piece or the pieces of information that you need?
Yeah. Yeah. Okay. Well, what I said and what the theorem said was that I needed something I called a B action, no, which is a pair of actions, one left, one right, which commute, no, and from that B action, we can get a representation. We can homogeneize. I don't know how to call it. Of the no, wait, of V, no. We can get a representation on each of the fibers by making an element G go to just conjugation. So given the B action, we can recover we recover completely a representation of G, and the other way around. So it's essentially unique. It's unique, not essentially unique. It's unique. So once you fix either one of these two guys, you get the other one, and automatically you get the multiplication, let's say from x, y of s, s plus t. No, okay, this is over x, this is over y. So what you get is e s y plus b x t e. No? So this is how you write the multiplication map from the B action. And since knowing the B action is equivalent to knowing one action, one proper action, not scratch proper, just one action, what this formula tells you is that what the action you already have, you get for free a unique super Lie group structure on the homogeneous or B-homogeneous bundle, whatever you want to call it. I don't know if I answered your question.
Then I'm not sure what you're trying to say.
Yeah, and these are codified by representations. Beta, let's say, are completely characterized by representations of G on the fiber of the identity. So you get one supergroup for each representation of G. That's the thing. Wait, what? Oh no! Well, yeah. Okay, I think I understand the question now. You get one. You get one split Lie supergroup over G for one of these. But yeah, you have to. What the theorem says is that once you have that one, no, yeah, there are many more different Lie supergroups. Exactly. Yeah, exactly. Which are infinitesimally equivalent. Yeah. Yeah, I'm sorry, I was confused by the question, but yes, what this says is that the infinitesimal, the tangential, the multiplication map are just codified by these B action, but the global picture is quite different. But the theorem tells us, the last theorem I showed tells us that we can intertwine them. That's the thing. But we have to construct from this B, which is what seemed to G star, no, S star, right? tensor G, no, which is invariant in this case, if you consider it as an element of a vector space. From this guy, one needs to construct a multiplication map that is associative. And the other way around, from an associative multiplication, one needs to get one of these that... Yeah, 99%. No, I mean, yes, we do. We're just verifying everything it's all right before sending it. But yes, we can recover from a given abstract multiplication map on a Lie supergroup, not necessarily split. One of these and the other way around. From this one, a multiplication map. But the details are rather cumbersome. That's why I didn't put them. I'm sorry. Huh? Yeah. Uh-huh.
Introduced that there are kind of bijective correspondence with these bihomogeneous vector bundles corresponding to these both coordinates. Classical neutral element. I find it very much in the recent resonance. Perhaps it is even can even be deduced from results by Stanislav Voronovich.
I don't know this.
Groups. So in
Wow.
1989, he published a paper titled Differential Calculus Pseudogroups, this is how he called
Okay.
groups. Actually, this is Hopf algebras that represent this basic underlying structure that can be, in general, very non-commutative. In your case, just smooth functions of the classical E group. And then a notion of bicovariant bimodal, which somehow utilizes this double action of the classical.
Okay.
And then he classifies bicovariant bimodals by this tangent space, which corresponds to the Lie algebra. And it turns out that it is a kind of representation and co-representation of the Hopf algebra. So I assume that in this case, where the underlying manifold is just classical, the module structure would be trivial, while the co-module structure that corresponds really to the representation would give you this magnitude automorphisms.
Okay.
It's a very nice one-to-one correspondence.
Okay, we'll like to read this. Yeah.
It's a kind of quantum supergroup.
Wow. Right. Okay.
And another foundational question. You mentioned the definition of morphism between two supermanifolds. So you use the conditions.
Yes.
There is a one
Yeah.
underlying plus.
Uh-huh.
And then there is a kind of companion algebraic map that goes in opposite direction.
Yes. Yes.
Just postulate the second one algebraic and deduce the first one.
Huh. That's a good question. No, I think you need both of them because what? Okay. Rn from Rm. This is the one. So you're asking if shouldn't it be completely characterized by this one? Well, no. The thing is that for all this to work, we need. I need to erase something. Just a moment. For all this to work, we are implicitly assuming that we have an inclusion map. No? From this to this. No? And this other part, I'm sorry, this other part will be the one that tells us how the algebra of smooth functions, of usual smooth functions, is embedded in here. And the important thing is that wait, I need some space. No, well, it's easier to just write this commutator that I defined. I mean, perhaps it would be completely evaluated Perhaps it would be interesting to know what kind of structure you get if you only consider this big phi, but the important part here is this part. This is what allows us to prove that they are differential operators. So probably you can get a new theory from just considering this one. But we like this one because they are, in some sense, very, very akin to differential operators, and we like that. No? But yes, I don't know. That's a very good question. No? I don't know if I answered your question, actually. Right, okay. Thank you.